All right, we're going to look at the least squares regression. We're trying to find the best fitting line. So when we look at number 10, this was the data that they had. And so I entered all of this data into list 1 and all the Y data into list 2. I did a second stat plot, turned it on, and I entered list 1, list 2, and a zoom stat, and I should have a scatter plot. Part A is going to look like that. Now you're going to fill in the dots. I'm not going to. I didn't feel the need to do that because you know how to do that. Now part B says that I need to select 2 points and find an equation of the line. So I happen to pick 2 points. These were the 2 points I picked. You might pick different ones. So I found my slope, and I put my slope and I put it in the point slope form, and I solve for y. So this is now my y hat, if you want to call it that. It is my predicted line, and I use the 2 points to get that. And I graphed this in y1. Now part C says to graph the line, and so that's what I did. Part D says determine the least squares line. Now we need to do a linear regression. So how are we going to do that? Well, I did stat, calculate, for linear regression, list 1, list 2. Since I want to be able to graph this, I put vars, comma y vars, comma function, comma y2, and then I hit enter. Now, what I ended up with in this linear regression is I ended up with this being my y hat. So y2 equals this. Now, if you'll notice, they're not exact, but they're not too bad. Now, because my diagnostics was on, I found this to be my R value. Now, that is E. In part F, what they asked us to do was to compute the sum of the squared residuals. So this is what we did. In part, right down here, in part F, what I did was I put list 1, list 2, and I put my linear regression line in. No, this is the one that so in part F, this is the one that I got with the 2 points. So I put that in list 3. And then in list 4, I subtracted the observed minus the predicted. In list 5, I squared it. And then in list 6, I summed them all up, because the sum of the residuals squared ends up being this number. Now, in part G, I'm going to actually do the linear regression that the calculator found. So again, list 1, list 2, this is the linear regression line that the calculator found. List 4 is y minus y hat. List 5 is taking whatever this value is and squaring it. And list 6 was adding them all up. So now what I have is the sum of the squared residuals, which is 4.0009. So now if you think about it, they're off, but not too bad. Now the linear regression has a smaller sum of residuals, so that means that this is the better fit than the one where I picked the 2 points. All right, in number 18, they said that a professor in stats wanted to know if there was a linear relationship between the amount of time a student studies for an exam and their exam score. Now she did a least squares regression line, and this is what she found for the least squares. Now predict the exam score of a student who studied 2 hours. So I put x equals 2, and I get the score to be about 65.7%. Now interpret what the slope is. Now the slope is this. So what I'm going to say is, now remember, it is the score over the hours studied. So for every hour you spend studying, your exam score goes up 6.33 points. Part C says, what is the mean score of students who did not study? If you didn't study, your time is 0. So if you didn't study, your exam score is going to be 53 points. Part D says a student who studied 5 hours for the exam score got an 81. And then find out what he would have gotten based on the y hat. So what I did here is I plugged in 5 and I got 84.7. He actually got an 81, so he was below that predicted score. Now, lesson 20 talks about explaining we have a carbon dioxide and energy production, and they gave us the predicted linear regression line. Y happens to be the 1,000 tons of CO2 emissions, and X is the 1,000 megawatts of energy produced. Now, to interpret the slope, that means for every 1,000 megawatts of energy produced, the CO2 emissions would go up by 0.7668 thousand tons. Part B says, is the y-intercept of the model reasonable? Now we have a negative 90, 11. So we got to find out if that's reasonable. Well, that means when there is no energy produced, this would be our emissions. And no, that doesn't it make sense, because you shouldn't have any emissions emitted if you didn't produce any energy. Part C says that the lowest energy producing country was Liberia, and the highest energy producing country was the United States. Would it be reasonable to use this model to predict the CO2 emissions for a country if it produced 6,394 megawatts? No, this is the highest. This is what we're saying that a country would be too high. Notice that's way outside of the scope, so it doesn't make sense to try and predict that. In Part D, China produced 2,410,000 megawatts of energy and emitted 2,680,000 tons of carbon dioxide. What is the residual or the error? So what I did was I took my y hat, I plugged in the x value, and I got this as my carbon dioxide. Well, it was actually this amount. So my residual is going to be this amount minus this amount, which is 841,023 thousand tons of carbon dioxide. This is the error, and that is above zero, so it is above the actual amount. All right, in 22 we're back to the black bears. Again, the data is written down there. And so the question is, find the least squares regression line, treating the total length as the explanatory and the weight explanatory variable and the weight as the response. So I did list 1, list 2, and I needed to find y hat. I entered the data. I did stat, calculate, line reg, list 1, list 2. I put vars, y vars function y1, and I entered it. I did that so that my equation is automatically put into the calculator. So when I did that, this is my r value, or my y hat value, 1.6942x minus 142.4709. Now what they ask us is to interpret the slope and the y-intercept if appropriate. Well, the slope says for every 1 centimeter increase in length, my weight increases by about 1.7 kilograms. Let's look at the slope, or the y-intercept. Now my y-intercept is negative, which means when I have no length on an American bear, it would weigh negative 142 kilograms. It's not appropriate because you don't have a bear that doesn't have any length to it. Now let's look at Part C. Part C says, suppose a 149 centimeter bear is captured. Use the least squares line to predict the weight. So here's my y hat. I plug in the values and I get 109.96, or about 110 kilograms. Now Part D says, what is the residual? In other words, what kind of error do we have? This is what we're predicting, and let's see if it's true. It says that what is the bear's weight above or below average for a bear of this height? So my residuals, my y, which says that it should weigh 85. This came from the table. So look up on the table, look on table, and you will see that a bear that was 149 centimeters weighed 85 kilograms. But this is what I'm predicting. So this bear is actually below average. All right, in number 28, we're looking at male versus female drivers. And there is a table on page 221 that lists the age range, the number of male licensed drivers in the thousands, the number of fatal crashes in the thousands, the number of female licensed drivers in the thousands, and the number of fatal crashes for those female drivers in the thousands. So what I have to do in part A is find a least squares line for males, and I'm going to have the male driver be the X and the fatal crashes be the Y. And then I have to do the same thing for the females. So I have males in list 1 and list 2, and I put females in list 3 and list 4. For males, I did a linear regression line, and this is what I found. And this was the R value that I had, so it looks like it's a positive association. For the females, I did the same thing, but I did a linear regression using L3 and L4. And this was the line that I got. Now the males, the slope says that for every 1,000 drivers, the fatality rate increases by 0.3428. For females, for every 1,000 drivers, the mortality rate or the fatal crashes increases by 0.105. Now when I look at this, they ask me in interpret the slope, which we did, and then how might insurance companies use this? Well, it looks like that females have fewer fatal crashes, so insurance companies might use this for lower rates for females versus males. Part C says, was the number of fatal accidents for 16 to 20-year-olds above or below average? So I look at males. This is what it actually was. I take the number of drivers and I put it in my linear regression line, and this is what it should have been. This is the number of fatal crashes it should have been, but this is actually what it was. So this number is above average. I did it again for 21 to 24-year-olds. This is the actual crashes. However, this many licensed drivers into my Y hat, and this is what the predicted fatal crashes should be. And then for 74-year-olds, this is the actual number of crashes. I put it again into my Y hat, and this is what it should have been. Now when I look here, this one's higher, so it's above average. This one's higher, so it's above average. This one is lower than what it should have been, so it's below average. So the insurance companies might say we're going to charge more for younger drivers, and then the next thing we have to do is repeat it for the females. So again, I use the Y hat for the female drivers, and I look, the 16 to 20-year-olds had this many crashes, and then I used this many drivers into the predicted. This is what we predict the number of crashes, but this is what we actually had. So this number is above what we're thinking we should get. Looking again at 21 to 24-year-old female drivers, this is the number of crashes, fatal crashes we had, and this is in the thousands. I put it into my predicted, and this is what it should have been. So again, this one's number is bigger, so this value is above our average. I looked at 70-year-olds. This is the number of crashes that they had. I put how many 74-year-old drivers there were, and this is what it should have been. So again, the number of crashes that 74-year-olds had was less. And so does it seem that the same relationship holds? And it does. And again, it would seem that younger drivers should be charged more than older drivers since they're in more fatal crashes.